Hello everyone, welcome to COMP125. We are going to continue our discussion about, in chapter 4, the building blocks. And this part we are going to focus on section 4.4, which is talking about how to create the simple circuits. Okay, so combinational circuits, or we simply just call them circuits here, are going to be, created from a couple of gates. And I'm going to actually just give you an overview that what we are looking for here and what we are going to actually learn about it at the end. At the end, we are going to see that how we can create a circuit to do, for example, addition, how we can create a circuit to compare two numbers, right? We are going to learn that how the computers can be created. So far, we have actually know that everything in computers can be represented as a sequence of 0 and 1s. And then we learned about the Boolean logic, and we learned that some gates can be created to represent, to actually, perform all those operators and or. And now we are going to use those gates to create circuits for us. We are going to actually see that how we can create a circuit that actually does, for example, addition for us, how we can compare two numbers. These are, the main goal that we are going to learn. Okay, so the thing is, circuit is going to be, as I said, is going to be a combination of, gates, and this is going to have a purpose. Okay, every circuit that we design is going to have some input that you passed on some input to that, and it's going to generate some output. For example, you added, two numbers and to a circuit and other circuit that will add those two numbers, and the output will be the result of that. Okay, so because the addition circuit is going to be very complicated for now, I am going to first focus on how we can create simple circuits. Okay, let me actually just show you an example. This is our very first circuit, and the thing that I would like you to actually focus here is that every circuit is going to be a combination of gates, right? It's going to have some input, a combination of gates, and some output. So at the end, the circuit is going to represent those Boolean expressions that we have talked about it. Okay, so for example, something like A and B or C, this is a Boolean expression, right? And this is going to actually, we can actually create a circuit for this one. This example that I'm showing here to you is a dummy circuit. This example is not going to represent this Boolean expression. I just wanted to actually give you an example here. But the thing is, this is a dummy example that doesn't do anything specific, but helps me to explain what is a circuit and how we can design a circuit at the end. Okay, let me actually just do a cleanup here, and let's just focus on this example that we have. So every circuit is going to represent a Boolean expression, and any Boolean expression that you write can be represented using a circuit. So if you have a Boolean expression, you can create a circuit for that as well. So it's just vice versa. Boolean expressions and circuits are equivalent to each other. And if I have a Boolean expression, I can create a circuit for that. If I have a circuit, I can just understand that what is the Boolean expression this circuit will be represented. So let's focus on this example, and I'm going to actually just show you that what is going to be the Boolean expression for this circuit. You can see this circuit has been created by just a combination of a couple of gates. I have an OR gates here. This is an OR gate, right? This is a NOT gate. This is an AND gate. And there is going to be another NOT gate. Okay, so get used to these figures. This is NOT, this is This is not, this is and, not, and this is or. Okay, so I have, you can see that as an input, I have two possible inputs here. I have one here A, and the other one that I'm calling it B here. You can see that in terms of, the electronic side, A is going to be actually, a wire that's coming to this circuit. B is another wire that's coming to this circuit. It's going to have some voltage that's representing 0 and false, right? So for us, we are going to actually just do a level of abstraction here and forget about those electronic parts and just think about it in this way that, okay, these are going to be some inputs. They are going to be true, false, and I'm going to have a couple of actually just gates that's representing the operators or, and not. So if the value of these numbers here that I put, these, 0 ones that I put here is just an example that shows you what would happen. For example, if the value of A is 1 is true, and the value of B is 0 is false, what would be the result of the, you can see that on the output side, I can have a couple of actually outputs as well. That here I have two outputs, one C and the other one is called D. So if A is 1 and B is 0, you can see that if I follow just, these wires, I can see that A and B, both of them have been actually inputted to this gate, which is OR. So it's just like what this part is doing is that A or, let me just show it this way, A or B. Okay, because A is 1, it doesn't matter what is the value of B, the result at this wire is going to be 1, right? And you can see that this wire is just going out as C, and so the value of C is going to be 1. On the other hand, for D, you can see that, okay, the value of B is passed through a gate here, which is not B, right? So it's actually doing not B. So because B is 0, the output on the output of this gate is going to be 1. This wire is actually just fed to another gate, which is AND, right? And the other one that actually just fed to this gate is going to be the wire coming from here. So what this wire is representing, this is the output of this gate. What I'm actually just representing here is A or B. Okay, so here what I have actually is going to be, let me just choose a different color for this one to maybe make it actually more readable. This is going to be A or B, and the other actually line that is coming here is going to be not B. So this is going to be not B. So this is the full expression that will be actually representing this line. Okay? And then whatever you get here, you are again feeding it to another gate, which is going to be a NOT gate. So this NOT will be applied over this expression. So now I can actually just write down the corresponding Boolean expression for all the outputs here. One output I have is C, right? The value of C is, if you actually just started from this line and going back and look, you will just reach to this gate, and the result is, so it's actually just telling you that C is going to be equal to A or B. Okay, as simple as that. For D, it's just more complicated. Again, you just go back over this wire and just follow and see that what you have. What you have here is, you can see that you have this gate, which is a NOT gate, applied over the input of that is going to be this expression. So I can just write down the value of D as well. This is going to be NOT applied over this expression, because this expression is going to actually represent what is what I'm going to have on this line. This is going to be A or B and not B. Okay, so whenever you have a whenever you have a circuit, just you can actually start looking at the output lines. For each output line, you can create the corresponding Boolean expression for that. Just to make it simpler, you can, in fact, start it from the input side and write down over each line that you have, just write down what you are actually getting from the input. So when at the end you are going to convert your circuit to a binary expression, you can just simply just write down all these, expressions that you have written over your circuit. So this is going to be the result. So you can see that, as I said, every Boolean expression can be represented as a circuit, and every circuit can be also actually represented as a Boolean expression. Okay, so as I mentioned, this example that I showed you is just a dummy example. This is not exactly what I'm just trying to say that this is not really doing anything specific, anything that I'm interested in. So now that you know how to create a circuit, we can, probably just still don't know how to create a circuit. You just know that every circuit can be actually, every circuit is going to represent a binary expression, right? A Boolean expression. So if I have a Boolean expression for the circuits that I want, then I can actually design my actual circuit as well. So what I'm going to show you here is the reverse of actually the thing. The thing is that I wanted to know how to create a circuit from a binary expression. So the very first thing that I do here is I would again need that truth table that I mentioned. Remember, I said that the truth table is going to be your friend. So what I'm going to actually do is that I would write down my truth table. For example, I know that I wanted to have a specific behavior on my output based on the input, right? So this can be represented using a truth table. So for example, I have written this truth table. I know that I need an output here, two outputs, output 1 and output 2. I know that for output 1, I wanted the values, for example, to be 0 when all the values are 0. For this line, I wanted the output 1 to be 0. I wanted the output to be 1 for this row. I want the output to be 0 for this row, and so on. So the thing is, I have the truth table. I wanted now to show you that if I have the truth table, how can I create the circuit based on the truth table? So what you do is just focus on one output at a time. So it's just like, for example, in this here, you can see that for example, C, I wanted to know that how can I get C? How can I actually just build a circuit for C? And then I will go and see that how can I, for example, create a circuit for D later on. So after you got the truth table and at each time focus on one output, what you are going to do is just look at the column, at all the rows of that corresponding column output column, and find all those rows that you get 1 out of it. Okay, so here for output 1, I can see that I have 1 here and I have 1 here. It just tells me that for the other cases, I don't want 1, and I don't care about the other actual cases, right? So I can say that for all those ones, if I created a set of gates that gives me 1, for the rest of it, it automatically will be 0. So you don't need to be worried about the zeros. I'm just trying to tell you that just think about those lines, those rows that you have 1 in. Okay, and then for each one, I am going to create a, an expression, a Boolean expression, a sub-expression for each one. And then for each of those, I will actually at the end create a circuit. Okay, so this one shows me that I wanted to have 1 on this row, which means that I wanted to get 1 when A is 0, when B is 1, and when C is 0. What does actually this tells me? It tells me that when all of these cases are true, when A is 0 and when B is 1 and when C is 0. Okay? This is a Boolean expression, right? But this Boolean expression cannot be simply converted to a circuit. Remember, we should be able to use the gates. How many gates I have? I have NOT gate, I have OR gate, and I have AND gate. Okay, so this part is good. For these parts, for actually getting AND between them, I can actually do that, right? But I cannot actually represent B comparing to 1 or C comparing to 0. What I can do here is that this, for example, A comparing to 0 can be represented as not A. So if the value of A is 0, this part is going to be 1. If the value of A is 1, this part is going to get it automatically will get the value of 0, right? So I'm trying to actually just tell you that this expression can be represented in this way, that not A and B. Okay, I don't be careful here. Instead of directly comparing B to 1, I know that when you compare B to 1, B is going to be 1. The result of this comparison is going to be 1, right? And if B is 0, the result of this comparison is going to be 0. So that's enough to just write it as B. And again here, I'm going to have not C. Okay? So how can I actually write that down? I mean, simplify that. That's going to be, I mean, in your textbook, I believe it actually showed in this way. A, not, and, you can see that and, remember I said that and will be represented using the dot as well. B and not C. So this is the final expression that I need. Or you can actually just represent it in this way. Not A and B and not C. Okay, so the sub-expression that I get for this line is going to be a combination of, putting and between the values, between actually all of these inputs. But sometimes you need to actually put not if the value is 0. If the value is 1, just forget about that. So here I have A as 0, so I just actually write not A, right? And B, I want B to be 1, so I just write down B without, applying the not. And I want the value of C to be 0, so I would write it as not C. Okay, so I can now get rid of all of these actually steps that I have written here. Just write it down as this simple expression that I have. This is going to be not A and B and not C. Okay, this is the final expression that, sub-expression that I wrote for this one. So this expression will be 1 only when the value of A is 0, the value of B is 1, and the value of C is 0. It would never get the value of 1 in any other cases. So if you actually just write down this one as a column in your truth table, you can see that this will only get 1 for this row. Why? Because you are just specifically saying that A should be 0, B should be 1, C should be 0. And the only row that's representing that is going to be this line. Okay? So for all of those rows that you have 1, you have to write down the corresponding sub-expression. So I have one more line that I have 1 in. I need to write down the sub-expression for this one as well. Look at the inputs. It's telling me that A should be 1, B should be 1, and C should be 0. So I can simply write it as A and B and not C. So this is going to be the sub-expression corresponding to this line as well. If you had more lines that you have 1, for each of them you write down the corresponding sub-expression. So now look at it from one level higher. I want to, in fact, create a Boolean expression that represents output 1. Output 1 will be 1 when this expression is true or when this expression is true, right? And be careful, I'm calling OR, okay? So what I need to do is just put OR between these two sub-expression. So at the end, here it actually just shows you this, the sub-expressions for each line here. And at the end, you just need to get the OR between all of those sub-expressions that you have written in the previous step. Okay, so that's it. The final Boolean expression that I get for output 1, this is going to be this one. So this is a Boolean expression. Now I can go and create a circuit for this Boolean expression. Okay, how can I create a circuit for this Boolean expression? Here it actually shows you the circuit for that. You can actually see that I have this, this parenthesis here, this sub-expression, which is the AND between 3 different values, right? 3 different actually wires. How can I actually apply that? There is no gate that will be applied over more than 2 inputs. All the gates that we had was actually AND 2 values or 2 values, right? So if you wanted to get something like this, the combination of, AND between more than actually 2 values, what you do is you need to actually combine them, first the 2 ones and then get the result and then combine the, fed them to another gate. So look at here. I have A, okay, which is actually applied over a NOT gate, will be actually fed to a NOT gate. So here on this line, whatever I have is going to be not A, or you can actually just show it in this way. Simpler. I think in your textbook it has been written in that way, just putting a bar over A. So this is going to be the not A. So not A, and this line is representing B. Okay, this wire, as you can see, it's coming from this part, so this is going to be B. So not A and B, so this is going to be not A and B. Now I wanted to actually AND the result with C as well to be able to get the this sub-expression. So what you are going to do here is you would need to get the value from C as well. Sorry, you are going to actually just use not C. I forgot that this is going to be not C, sorry. So instead of getting actually a line from, you are getting the line from C. So here this part is going to be not, why I'm writing C. A. Okay, so here the output on this line is going to be not C, right? Not C will be coming and fed here. So you are going to have not C here. Not C, and the result here, which is going to be not A and B, will both of them fell to this gate. So the result of this gate on this line is going to be not A and B and C, not C. So this is going to be exactly this sub-expression that I need. Okay? After you are done with that, you would actually create a circuit for this one. Again, I have 3 possible values to be AND together, right? So I would actually create them two at a time. So first A and B will be fed. You can see that A is coming from here. It's not passed through any gate. And B is coming from here. It's not passed to any other gate. So the result of this line is going to be A and B. And then you would get the value from not C. You can see that this is coming from this not C that has been calculated here. So you have not C. It will be this line, and this line will be fed to this gate. The output is going to be, on this line is going to be A and B and not C. Okay, so I have created this, combine all of the gates to calculate this line as well. These 2 lines will be fed to another gate that represented, this is going to be an OR gate, right? So the output 1 has been actually just created. This is going to be the full circuit for output 1. So if you remember the very first truth table that I had, we had 2 columns, output 1 and output 2. I'm done with output 1, then you have to actually just apply that for output 2 as well. You can see that I'm going to skip that from this example, but it's just clear that, okay, you again just this time focus on output 2. Just let's review the steps. You find all of the rows that you have 1 in. So this row, this row, this row, and this row. For each one, you would write down a sub expression, right? So you look at the values. You can see that all the 3 values here are 0. So the sub expression for this part is going to be something like this: A and not A and not B and not C. For this one, write down a sub expression. This is going to be not A and B and not C. Okay, and another sub expression here, which is going to be not A and B and C, and another sub expression here, which is going to be A, because A is 1, B is 1, and B and not C. Okay, after you get all of this sub expression, you get the OR between all of this sub expression. Why? Because you wanted the output 2 to be 1 if any of these lines, any of these expression became 1. So now we are actually applying OR. Again, here you can see that, for example, I have 4 values that I need to get OR between them. So you should combine them 2 at a time. So you can combine 2 of them, you can combine the other 2, and at the end you would actually just apply that. Let me actually just show you. If you have 3 possible lines and you wanted to actually just, 4 possible lines, and you wanted to apply a binary gate both between them, what you can do here is that, for example, just combine these 2. It doesn't matter if it is or if it is and, because they are binary gates. You can only just pass 2 of the results to each one. So you can, for example, just combine these 2 as well, and then give the results to another gate, again an OR gate, and this is going to be the final result between all of these lines. Okay, if it is and or if it is or, it doesn't matter. So this is the way that we actually combine to get apply the or and between more than 2 input values. So this algorithm that I just explained here is called the sum of products circuit construction algorithm. This algorithm is quite simple. You can see that whatever is the if you know the truth table, you can simply create the Boolean expression for that, and from the Boolean expression you can create the final circuit. The algorithm is important for us because most of the time when we are going to actually design a circuit, we don't know the Boolean expression corresponding to that. This algorithm helps us to simplify this process, and from the truth table, because what you know is the truth table. You would know that, okay, if I have these specific inputs, I wanted the output to be, data specific, whatever is the output that I want. So it is easy for us to design the truth table because the truth table is exactly the behavior that I would expect from my circuit. So I know what I want, but I don't know how it can be represented. So if you know what you want, you write it down as a truth table, then from the truth table, using this sum of products algorithm, create a Boolean expression for that. From the Boolean expression, you can create a circuit. Okay, so now that you know how to create the circuit, we can then actually go and learn to how we can create a circuit for some actual tasks, for example, adding two numbers or comparing two numbers. Just before finishing this subsection, I wanted to also talk about this fact that the sum of products algorithm is very simple and it always works, but there is a downside in that. There is a drawback for that the result of the sum of product is not optimized. In fact, the sum of product, as you have already actually seen, it might actually resulted in a very big circuit with many gates. So, for example, in the previous example that I had, this circuit was the one that we designed for output 1, okay? If you think about it, it is possible to create a circuit with just two gates for the same, to getting the same output. And this is showing you that optimized circuit. Okay, the sum of products, of course, is not going to give you the optimal circuit because we always wanted to minimize the number of gates, because having gates is going to be costly. You are going to actually just take some space on your chips when you are creating these circuits. So definitely we would prefer the circuits that they are using less number of gates and simpler. Although the sum of products is not going to give you the optimal answer, it's just telling you that it is possible. This is something that's important for us in this course. But in reality, there is a big line of research over this fact that how we can actually optimize the design of the circuits and using the minimum number of gates to design a circuit. But anyway, this is beyond the scope of this course, and I'm not going to focus on that. Just wanted to mention it that this algorithm is not going to give you the optimal circuit. So here, let's actually do one practice that I have a truth table here. I wanted to create a circuit for that. If you look at this truth table, the truth table only have two inputs. It doesn't matter how many inputs you have. Based on the number of inputs, you write down the truth table, and then the algorithm is the same. You just look at all those rows that you have one, write down the sub-expression for each one, and then get the OR between all of those sub-expressions. So if I look at the output, you can see that I have 1 here and 1 here. So for this one, I need to write down a sub-expression. So the sub-expression for that is going to be true when A is 0 and B is also 0. So the sub-expression for that part is going to be not A and not B. Okay? This is for the first one. And for this one, you can see that the value of A is 1 and the value of B is also 1. So the sub-expression for that is going to be A and B. Okay, and then I would get OR between all of the sub-expression. I only have 2 sub-expressions, so I put OR between them. So this is going to be the final Boolean expression that I need. How to design a circuit for that? Let me actually just write it down here. It's going to be very simple. So this is going to be a line coming from the input A, another line coming from input B. You can see that I need not B and B, both of them. So I would create one line for not B by passing it over a NOT gate, and another line for not B again, take B and passing it to a NOT gate. Okay, so what I'm doing here is, okay, to create this sub-expression, I need not B, not A and not B, and I need to pass them to an AND gate. So this is an AND gate, and I need to create this sub-expression, which is the AND between A and B. So I would need another gate AND here. This is going to be this sub-expression, and then I need to apply OR between them. So this is going to be passed, both of these will be passed to another gate, which is going to be an OR gate. And this is going to be the result. So one thing very actually interesting about this, the truth table, is that in fact it is showing a very interesting, operator. We have a name for this. This is going to be called XOR. And basically the meaning of that is exclusive OR. It's just saying that if you look at the values of the output, it is 1 when the values of the inputs, all of the values in input are the same. So it is 1 when A and B are both 0, and when A and B are both 1. And nothing else. So it's just like, it shows this behavior that, okay, when A and B are both of them the same, I wanted the output to be 1. Otherwise, I want the output to be false, as 0. Okay, so it's just like if A and B, both of them agree to each other, it doesn't matter if they are 0 or if they are 1. If they are the same, the output will be 1. And it is a well-known, again, Boolean operator. Although we have actually talked about and or and not, and or and not are the basic operators and the primitive operators. This XOR can be actually represented using and, or, and not. And you can actually see that I can actually write down a Boolean expression based on and, or, and not. But because this is something well known, it's just like, for example, multiplication can be can be created, can be calculated using a couple of sums. XOR can be calculated using the and, or, and not. But this is a well-known operator. Here is another example. In fact, this is just showing you XOR over 3 values. It's just like XOR between 3 input lines. So the truth table that I have is going to have 8 lines, as you can see, and 3 input columns. And if you look at the output, you can see that I have in the output 1 only when all the values of A, B, and C are the same. So I don't have 1 anywhere else. But you can just forget about the meaning of that. Just stick to that sum of product algorithm. Write down the Boolean expression for all the rows that you have 1 in and get the OR between all of them. But let's actually just write that down. You can see that for this line, the value of A, B, and C all are 0. So this is going to be not A and not B and not C, and this line all the values of A, B, and C are 1. So this is going to be A and B, A and C. And so these two Boolean expressions, you need to get OR between them. So at the end, what I have here is going to be not A, not B, not C. Get the OR between them, A and B and C. And now I can actually design a circuit for that. So this is going to be, for example, this is A, this is B, and this is C. I would get a line from each one. And apply the not over them because I need not expressions here. Okay, you need to get and between all of these. So A and B, and then you would get C and apply another gate and. So this is going to be A and B and C. So this is going to give me this sub-expression. And then you apply an AND gate here. And another AND gate here. So this is going to be not A and not B and not C. So the result will be actually passed to an OR gate, an OR gate. So this is going to be the final circuit for this big XOR. Okay, so now that you know how to create a circuit from the truth table, we can go and talk about more interesting circuits, some actual circuits. In your book, it has been actually two main circuits has been discussed: how to compare two numbers, compare for equality, and addition, adding two binary numbers. So first, I'm going to talk about how to compare two binary numbers. This is going to be very exciting. Now you can actually see that how we can really create a circuit to compare two binary numbers and see that if they are true or not. If they are true, the result, the output will be 1. If they are equal, the output will be 1. And if they are not equal, the output will be 0. Okay, so the main thing that I wanted to actually design is that if, for example, you have an input like x, which is a binary number like 0, 0, 1, 0, 1, and another binary number like y, which is again going to be 0, 0, 1, 0, 1. So if you pass these two to your circuit, the circuit is good. The result of the circuit, the output should be 1, and because they are equal. And if, for example, you passed another input like this, the comparing x and z, if you pass x and z to your circuit, the output will be 0. That's representing that they are not equal. And okay, so if you are comparing two binary numbers that, for example, each one has 5 bits, each one has 8 bits, doesn't matter how many bits that you have. Each of these bits are going to be one line of input, right? So if you have 5 bits, you can see that it's just like you have, for x, you are going to have 5 inputs. For y, you are going to have another 5 inputs. So at first, because it's going to be complicated to talk about, binary numbers with more than one bits, let's first focus on creating a circuit to compare two binary numbers that they only have one bit. And then we will actually extend it and create a circuit that compare two binary numbers with n number of bits. Okay, so that one bit version is going to be called 1CE. I'm going to actually just show it as 1CE, which is telling you that there's going to be a compare for equality circuits, that's CE, and 1CE means that this is going to only compare, two bits. Okay, so to create a circuit for this one, I need to design the truth table. So A is going to be one input, B is going to be another input, right? A is just one bit, so it's going to be either 0 or 1. B is going to be 1 bit, it's going to be either 0 or 1. It gives me a full truth table with 4 rows. I wanted the output to be true if both values A and B are the same, if they are equal. So if they are both 0, I want the output to be 1. And if they are both 1, I want the output to be 1. On the other cases, for example, when A is 0 and B is 1, they are not equal, so the output is 0. If A is 1 and B is 0, they are not equal, again, the output is going to be 0. Okay, so this is the way that you design. You have to design the truth table based on the desirable output, desirable behavior that you would like to see in your circuit. So this is a part of the design of the circuit. You have to design the truth table based on the desirable behavior that you want. Okay, so this is going to give me a truth table. And we have already seen this truth table before. Remember, I have talked about it as XOR. This is exactly that example that we have seen here. Okay, so it actually just shows you that now we can just apply that sum of product algorithm. You can look at you only have one output. You can look at all those rows that you have 1 in, write down a Boolean expression for each one, which is the AND between the values, and you get the OR between all of them. So this is going to be a Boolean expression for this part, and this is going to be the Boolean expression for this part, and you get OR between them, and you actually design the circuit for that. Okay, I have written and showed you that circuit here, which is going to be represented in a much nicer figure here. I mean, it's better than my handwriting, of course. You can see that A and B has been passed to this and not A and not B, not A and not B has been passed to this gate, and both of these two has been passed to the OR gate, so this is going to be the output. So this is a full 1CE circuit. So this is a compare for equality circuit that compares only binary numbers with 1 bit. Okay, so now the question is, what if I have binary numbers that they have 5 bits, that they have 5 is not really actually an actual number of bits to represent a binary representation in computer. So for example, how can I create a circuit to compare two binary numbers that has 8 bits or 16 bits or 32 bits or 64 bits, any of them? Okay, so it doesn't matter how many bits you have, let's just call it n. How can I create a circuit to compare two binary numbers that they have n bits? So if you have n bits for your number, let's actually just call it, for example, x. X will be represented in this way, that x, this is going to have n bits. So first bit, let's just use the subscriptions, for example, x sub 0, x sub 1, x sub 2, until x sub n minus 1. And you have another number like y, that this is going to be y sub 0, y sub 1, y sub 2, until y sub n minus 1. So if I'm comparing these two binary numbers x and y, I wanted all of these bits to be equal to each other. Okay, so basically what I need to do here is I need to compare x sub 0 with y sub 0. They should be equal. X sub 1 should be equal to y sub 1. X sub 2 should be equal to y sub 2 until the last bit that they are equal. All of them should be equal. So now you can see that I already have a circuit to compare one bit. So I can use this circuit to compare, to do this comparison between all of these bits. So I need n circuits n circuits of which type? N circuits of type 1CE. Okay? And the result of all of them should be true to get true at the final. Okay, so this can be simply shown in this way. You can see that I'm comparing the first digits or the first bits using one 1C circuit here. A sub 1 and B sub 1 will be actually compared here. The third bits will be compared here. The fourth bits will be compared here until the last bits that will be compared here. Okay? All of these outputs should be 1 to get 1 on the final output. How can I do that? There is no gate that gets the AND between all of these n different wires that I have. So I will combine them 2 by 2. So these two will be actually just passed to an AND gate here. These two will be passed to an AND gate. And, you combine each of those two together. And then the result of that will be AND. You need another actually AND gate here. Just continue and get AND between all of these until at the end you will get only one line of output. So you can see that you would need a couple of actually AND gates in between to combine all of these n outputs that you get from the one comparisons for equality circuits that you get. And at the end, this is going to be the full circuits that compare two binary numbers with n bits. And we are done. Okay? This is actually nice to see that these levels of abstraction here. You know that how you can actually create a simple circuit and how you can create the gates. These gates are created from the transistors. But when I'm actually creating this big circuit, I would do a couple of actually levels of abstraction, and I forget about all those details of the voltage, transistors, and all of that. You actually designed a very simple circuit, and then you are using this very simple circuit inside the larger circuit that you are actually just designing. Okay, now let me actually just show you another example. We are going to design another circuit, a little bit more complicated. We wanted to create a circuit to add two binary numbers. Okay, so before actually showing you the circuit, let me give you the idea of adding two binary numbers. Adding two binary numbers, in fact, is just following the rules for adding any two decimal numbers. For example, if you have a two decimal numbers like, let me actually show you something like, for example, you are adding 19 to, for example, something like 95. Okay, these are decimal numbers, right? But just remember how we are adding these two numbers together from the elementary school. You are adding them digit by digit, right? So you would get 9 and 5 together. The result is going to be 14. So the result is going to be 14. 9 plus 5. So how you write it? You would write 4 here, and you would have one carry digit that you actually just pass it to the next when you are actually adding the next digits, right? So now you are adding 9, 1, and 1. So here you can see that 9, 1, and 1, the result is going to be 11. So again, you are going to write down 1 here, and you are going to pass a carry digit, a 1 carry digit to the next digits. So you can think of it as, okay, there is going to be a 0 digit here and a 0 digit here. You add them all, the result is going to be 1. So although the inputs for this addition had only 2 digits, the result is going to have 3 digits, because it is possible that, for example, in this case, that you can see that I had 1 carry digit at the end that has been actually written in this way, right? For the binary addition, everything is the same. The only difference here is that your representation is binary, not the decimal representation. So let me show you this addition between these two binary numbers here. I have a binary number here, and I have a binary number here that I'm adding them. So when you are adding these two numbers, you just, let me see, it's just a little bit, probably if I pushed it this way, this is going to be better, okay? So everything is aligned now. 1 and 0 will be added together. 1 and plus 0 is going to be 1. This is less than 2, so I don't have any carry digit. So it's just like the result has been written here, and the carry digits is, in fact, there is going to be a carry digit, but that carry digit is going to be, or carry, let's call it carry bits, is going to be 0. And then you are adding this one, and the carry bits is going to be 0. So 0, 0, and 1, the result is going to be 1. So you write it here. Because it's less than 2, there is going to be a 0 carry bit. So now here you have 1, 1, and 0. 1, 1, 1 plus 1 plus 0, the result is going to be 2, right? So 2 in the binary representation will be 1, 0. Okay, so this is going to be the digit that you write down here, and this is going to be the carry bits that you passed. So this is going to be coming here. Okay, so for the next line, again, you can see that I have 1, 1, and 1. The result is going to be 3. 3 will be written as 1, 1 in binary representation, okay? So this is the digit or bit that you write down here, and this is the carry bit that you passed. That this one is going to be here. And then you are adding it here. You have 0, 0, and the carry bit, which is 1, the result is going to be 1. And the carry bit here is going to be 0 for the next bit, 0, 0, and the carry bit 0, the result is going to be 0. Okay, so this is what we want to design. We wanted to design a circuit that you passed it two binary numbers, but each one is going to have n bits, and if you pass these two, it should be the output. It would look very complicated now, but what we can do is, again, do exactly as we designed the compare for equality circuit. We would create a circuit that just add two binary numbers that has 1 bit, okay? And then we will extend it to binary numbers that they have n bits. So to be able to do this addition, creating this simpler circuits, although we have only, I mean, two binary numbers that they have, each one has 1 bit, but we should also take care of the carry bits as well. So unlike the previous circuit, for us, this circuit is going to have 3 inputs. This is going to be one input, this is going to be another input. Let's just call it A sub I and B sub I, because we are going to design one circuit for adding each digit or each bit of the number. And there is going to be a carry bit as well. Okay? So let's me, okay, we wanted to design this one circuit that's just adding one of these additions. Just for example, let's just call this addition to be a circuit which adds the ith bits. Okay, we wanted to create this circuit. So now you can see that, of course, the inputs for this one is going to be one bit from A, one bit from B, and the carry bit, which is actually coming from the previous, adding the previous digit. So this is the circuit that we are going to design. We call it one add circuit. And again, remember, the very first step is to design the truth table. So, okay, how to design the truth table? Although the truth table is given here to you, let me actually just explain it a little bit to tell you that what's going to be happening. So this is going to be A sub A, B sub A, and the result is going to be one digit which is coming here, one bit which is coming here, and one bit which is actually just passing to the next level, right? This is going to be that carry bit. Okay, so the possible values for A and B, A sub I and B sub I, both of them are binary, right? And the carry digit, no, I just actually screwed that. I forgot that there is going to be another input here. There is going to be an input CI, which is the carryover from the previous addition, which was actually A sub I minus 1, B sub I minus 1. From adding these two, you get an input here as well. And then you created an output, which is actually coming as the carry of the next level, the carry bits for the next level. Okay, so what is going to be the possible values for A sub I, B sub I, and C sub I? All of these are going to be binaries, right? I have 3, just from now on, just forget about this. I just wanted to design the truth table. So I would design my truth table with 3 input columns with all of the possible values for A sub I, B sub I, and C sub I. So it's going to be all these 8 rows that I have. Okay, so for each one, let's just see that what I would expect to be S sub I and what I would expect to be C sub I plus 1. Okay, if A sub I is 0 and B sub I is also 0 and C sub I is 0, when you are actually adding them, of course, S sub I is going to be 0, and that carry digits that you pass is going to be 0 as well, right? I actually just write them down here on the output side. If A sub I is 0, B sub I is 0, but carry from the previous level is 1, now the output is going to be, S is going to be 1, but still this carry over is going to be 0, right? This is exactly the behavior that I would expect here. S sub I is 1, C sub I plus 1 is going to be 0. When a sub I is 0, b sub I, this line, a sub I is 0, b sub I is 1, but c sub I is 0. Again, the result should be the same. S sub I should be 1, but there is no carry bit, right? How about this line? A sub I is 0, b sub I is 1, and c sub I is 1. So this is the case that the result is going to be 2. So of course, the output is going to be, S sub I is going to be 0, but there is going to be a carry bit. So C sub I plus 1 in this case is going to be 1. Okay, let me actually just check the next row. You can see that to design the truth table is really important and you should take a good care of it. Just go over each line, think about all those possible inputs, and think about the output that you would expect. So A sub I is 1, B sub I is 0, C sub I is 0. There is no carry from previous, so the result is going to be S is going to be 1, and the carry, there is no carry, so carry is going to be 0. The next case is that A sub I is 1, B sub I is 0, but there is a carry from previous level. So S again is going to be 0, and there is going to be a carry bit for the next level. A sub I is 1, B sub I is 1, but there is no carry from previous. So again here, the result is the result of adding 1 and 1 is 2. So the digit is going to be 0, S sub I, and the carry bit is going to be 1. And the final case is that all of them are 1. So it's just like the result is going to be 3, which the S sub I is 1, and there is going to be a carry digit as well. So you are done with designing the truth table. Okay, when you are done with the truth table, you can simply just apply that sum of product algorithm. Look at each output. For each output, we will apply the sum of product for each output line and create a circuit for each one. So here, it actually just shows you the Boolean expression for S sub I, which is exactly coming from this truth table that we have written. Let me just clean it up here. Okay, the only thing that I care about is just looking at those rows that you get 1. For each one, write down a sub-expression and then get OR between all of them. So if you do that for both both these columns, this one and this one, you are going to get this expression for S sub I and C sub I plus 1, sorry. Okay, when you got the Boolean expressions, you can create the full circuit. This circuit is going to actually just show you what would happen to S I. Okay, if you wanted to see the full circuit, this is going to show the full circuit. This is the output of S sub I, and this is the output that's going to be C sub I plus 1. These are the inputs and these are the outputs. So this is going to be the circuit for the complete circuit for one add circuit. That's just adding one bit of a binary number. Okay, it might actually look very complicated, but you know how we actually get here. So don't worry, from now on I can see this one just as a building block, that I would understand it, write it as one add this circuit, that what you are passing to this one is going to be A sub I, B sub I, and C sub I, and what you are getting out of it is going to be S sub I plus 1, sorry, S sub I, and C sub I plus 1. Okay, so these are the inputs, these are the outputs. This is the circuit that I have. So when we are done with this one one add circuit, I can actually use this one add circuits to be able to write down the full circuit for adding in two numbers of n bits. How can we actually do that? The thing is, you have two numbers like this and this, right? If you write it down, this is going to be like this one. A sub 1, a sub 2, until a sub n minus 1, right? This needs to be added to b sub 0, b sub 1, b sub 2, until b sub n minus 1. If you are going to add this, in fact, a sub 0 and b sub 0 will be sent to one circuit, and you might actually just say that what is going to happen to c sub 0? C sub 0 will be initialized as 0. Okay, that's easy because there is no carry digit when you are adding the least value digit, right? And the output here is going to be s sub 0 and also c sub 1. That's going to actually pass to the next level. So what I need to do is just put one circle for each of these digits, one add circuit. Okay, so the final result is going to actually look like this. Okay, this is going to be that number A with n bits, number B with n bits. What you are doing here is that you are going to add a sub 0 and b sub 0 together. Okay, so this one will be sent to this circuit and this one will be sent to this circuit, and the initial carry is going to be set to 0. Okay, so all these three inputs will be passed to one circuit. You know how to design this one. And the output is going to be S sub I and S sub, for this one is going to be S sub 0. Okay, S sub 0 and C sub 1. So where this S sub 0 is going to be, so this is going to be your output. This S sub 0 is going to be coming and written as the first bit in the output. And then this output will be passed as input to the next add circuit, which not only gets this one, but also will get A sub 1 and B sub 1. Okay, the output of this one is going to be S sub 1, which will be written as the second bit of the output number. And the other output is C2, which is passed to another add circuit. And you just actually just continue and finish the full circuit. You can see that we need n number of one add circuits to be able to add two binary numbers with n bits. And this is just, you know, the final circuit that we have designed for this. Okay, so there are actually, this is going to be the end of the, I believe in my textbook, which is edition 7, this is going to be the end of section 4.2. And so just make sure that you finish the 4.4. This is going to finish the section 4.4. Just make sure that you do the practice questions at the end of the that section. So the last section that I wanted to cover and finish here is that so far we have learned about we learned about the binary representations first, then we learned about the Boolean logic, then we learned how to created gates from to represent the Boolean those Boolean operators, and then we saw that how we can create some complicated circuits using the gates. we saw some very interesting circuits for comparing two numbers or for adding two numbers. And so not only the comparisons and, for example, the arithmetic, circuits, we also need some other type of circuits that helps us to do we call them actually control circuits. So in section 4.5, we will learn about two other type of circuits. They are not arithmetic circuits, actually. They are not, for example, comparing two numbers or adding two numbers, or we can design, for example, a circuit for subtraction, for example. We can design a circuit for different type of actually arithmetic expressions. But here in this section, we are going to talk about a different type of circuits. These circuits are going to help us to do the, to make the decisions. That in computer, not only we need to do the arithmetic calculation, we also need to, for example, sometimes choosing from a couple of different possibilities. Right? This type of actions can be done using control circuits. And we are going to learn about two control circuits. The first one is called multiplexer. So this figure here actually shows you what the multiplexer actually do, what we would expect the multiplexer to do. The input to the multiplexer are two types of inputs. You can think of it in this way, that the multiplexer, the task of the multiplexer is to help to choose from some input. So for example, you have 2 power n different input lines, okay? And you wanted to choose one of them, okay? So but which one you are going to choose? This is going to be your decision, right? So this is going to be another set of inputs. So not only you have these inputs, you also are going to have some selector line. So you have n lines. You can see that these n lines, because you have n lines and each line is going to be, a 0 or false, at the end it's just like you have n bits. With n bits, how many options you can show? You can show 2 power n different possibilities, right? So exactly these lines tells you that which input you are going to choose. So for example, if your input sectors, for example, if you have a multiplexer with 3, let me just show you a bigger picture. Just assume that you have a multiplexer with 4 input lines, and you wanted to actually choose, for example, do I need input 0, input 1, input 2, or input 3? There are going to be 2 lines that helps me to select. So these selecting lines, if you pass 0, 0, the multiplexer will get the input. This line will actually just, it's just like it choose from all these 4 different inputs to redirect this line to the output. If, for example, in your selector you shows, for example, 0, 1, it means that you want the line from input line 1 to be redirected in the output. If it is, for example, 1, 1, it's just like you wanted to line 3 to be redirected in the output. So multiplexer is just, allow you to choose among a couple of input lines. So how we can design a multiplexer? So exactly just like what we did in designing, addition or comparisons. You should write down the, the truth table, and from the truth table you create the circuit. So you should write down the truth table if you are going to create a multiplexer of size, for example, 1, then you can create the multiplexers of size bigger. So this figure shows you this very simple multiplexer that has only one selector line and has two input lines. So this is a very simple form of it, right? Of course, when you are actually designing more complicated one, it would be much more complicated. But your textbooks just, because I wanted to give you the idea that how you can design it. And for the bigger one, you can just think about it, how to design a bigger actually circuit. So let me actually explain that how the 1-bit or 2-input multiplexer would work. The 2-input multiplexer, of course, you have two inputs, right? A and B. You have one selector line. So if the selector line is 0, the line that shows the input 0, this line should be redirected in the output. You want A to be in the output. Okay? Be careful. You want A. Whatever is A, I don't care what is A. Maybe it is 0, maybe it is 1, whatever it is. I wanted A to be redirected in the output. I wanted to see A here as a result. If the selector is 1, I wanted to have B on the output line. So if you look at this design, you can see that the selector line has been actually passed here and passed through the NOT gate. So it's just actually will be not, let me actually just show that as S, not S. So if the selector line is 0, this not S is going to be 1, right? When S is 0, not S will be 1. So this line will carry the value 1. So I don't care that what is the value of A. Value of A, it will be actually just passed here. And in the output of this AND gate, what do you have? What are you going to get? You can see that because this is an AND gate, it's just like you have 1 and A. 1 and A, the result is going to be A. The reason is that if A is 1, so if A is 1, the output will be 1, output. If A is 0, the output will be 0. Because when you are AND 1 with anything, it's just, just like you are multiplying a 1 to something. So the result here is going to be A. So A will be get out of this line. Okay? What would happen on this line? If the selector is 0, you can see that if you follow this gate, you can see that the value that is passed to this gate is the selector and B. Okay? Because the selector is 0, the output on this line is going to be 0. Right? It's just like you are passing 0 and A to this gate OR. Because this is an OR gate, whatever you are getting on the output is going to be A. Because because this side is 0, the result of this gate will only be true if A is true. If A is false, it will be false. So again, whatever you are getting as the output is going to be exactly A. So if the selector is 0, the output will be A. I don't know what is the value of A, but this is exactly what I would expect from the multiplexer. I'm just saying that if the selector line is showing 0, I wanted the output to show A. Okay? Let me just do a couple of, clean up here. And show you the other case. What would happen if the selector line shows, what would happen if the selector line shows 1? If this, let me just use a different color. If the selector line shows 1, so again, what would happen here? S is 1 this time, right? Not S will be 0. Okay, we can see that this line will be 0. So what I'm getting on this side is going to be 0. Because this is 0, passing to not, it doesn't matter what is the value of A. The output will be definitely 0. It's just like you are disabling the output here. So the value that is passed from this line is going to be 0 when the selector is 1. You can see that I'm showing it using blue. So when the selector is 1, this line is going to be 1, right? And you are passing B as well to that. So the output on this side is going to be B when the selector is 1, because whatever is B will be the result of this gate. So it's just like you are passing B on this line. You are passing 0 from that gate, and you are passing B from that gate to this OR gate here. So what will be the output? Because this is an OR gate, whatever is the value of B will be the output. Because the other line is 0, so the output will depend directly on B. So you are going to get B on the output. And this is covering both cases. When the selector is 0, you will get A. When the selector is 1, you will get B. So this is a multiplexer with only 2 lines of input and 1 selector. Now we can actually just think about it, how to create a multiplexer with n bits. That I'm going to actually skip it because it's going to be a little bit complicated, and we don't really need to know all those details. Just wanted to show you that it is possible to create this kind of actually circuits as well. The other control circuit that's covering in your textbook is decoder. Okay, decoder is kind of completely, the reverse of multiplexer. In the decoder, instead of having 2 power n inputs, we are going to have n inputs. And in the output, we are going to have 2 power n output. So in fact, in the decoder, it's just like, for example, you have if you have 2 lines of input, 2 lines, on the output, you are going to have 4 possible lines. And what does the decoder actually do? I mean, logically, is that, so whatever is the number that's represented using these input lines, for example, if the input lines are 1, 0, if you think about it as a binary number, it's going to represent a number 2, right? These lines on the output are going to basically just represent 0, 1, 2, and 3. So it's just like you are decoding from, these 2 bits here that you have. You are decoding it, and what you are getting, for example, if you have 1, 0, if you code 1, 0, this will be represented 2, right? So the line 2 will be actually activated. So just the thing is, if you get 1, 0, the line 2 will be activated. Or for example, if you get 0, 1, so 0, 1 will be representing 1, right? So if you get 0, 1, line 1 will be actually activated. It just means that this, what I'm saying that by, activating, it means that this line will be 1, and the rest of the lines, all of them are going to be 0. So at each time, based on whatever you have as the input, just one of those 2 power n output will be activated. Just one of them will be 1, okay, and the other will be 0. So here is a circuit, a very simple circuit for decoder that is a decoder of 2 to 4. 2 to 4 means that you only have 2 inputs and the output is going to be 4. Why 4? Because 2 power 2 is going to be 4. Okay, if you have 3 inputs for your decoder, this is going to be an input, decoder of size 2 to 8. Okay, sorry, 3 to 8. If you had 4 inputs, it's going to be 4 to 16. The number of outputs will be 2 power n. So, but let's actually see that how this one is going to work. You can see that I have the input 1 and input 2. Input 1 is showing the left digit, input 2 is showing the right digit. So let me actually just show you that what would happen if I have 0, 0 on the input 1 and input 2. If you have 0, 0, now you can actually just follow the lines. You can see that you would have 0 on this line, you would have 0 on this line, so this line will be 1, this line will be 1, this line will be 0. And look at these actually gates that I have at the end. This gate is getting 1 and 1, right? Because this line is coming from here, and this line is coming from here. So now you can see that because I have 0 and 0, the output of this line will be 1. Okay? And be careful, the rest of the output should be 0. And let's look and see that what I'm getting from each of these lines, each of these gates. Here, what I'm getting is, you can see that this is coming from here, right? So this line is going to be 0. But this line is going to be 1. 1 and 0, the result here is going to be 0. Okay, so far, so good. How about this gate, the output of this one? This one is coming from the input that's passing here is going to be 1 because it's coming from this NOT. But this line is going to be 0, right? It's coming from here. So the output of this line is going to be 0 as well. How about this gate? The input of this gate here is going to be 0. The input of this gate here is going to be again 0. So of course the output here is going to be 0. So you can see that by having the 0, 0 as input, the only line that will be 1 is going to be this line. The rest of the lines is going to be 0. Let me show you another example using a different color. For example, let's just see that what would happen if this is 1 and this is 0. So if you look at the output gates, you would guess that, okay, this number is going to be represented to line, right? So you would expect that gate 2 should be, gate which is corresponding to the number 2 should be actually be activated. If you look at this gate, the input that's coming from here is coming from this side, okay, which is exactly, you have 0 here, so you have 1 after the NOT, so this line is going to be 1, right? And the other line is coming from here, which you exactly are going to have 1. So the output from the input here is going to be 1 and 1, right? So the output here on line 2 will be 1. How about the rest? You can see that the rest of the lines are going to be, the output of the rest of the gates are, all of them are going to be 0. Because this line is 0 and this line is coming from 0 as well. This line will be, this line is coming from here, so this line will be 1. But unfortunately, this line is going to be 0 coming from this line. So this one is going to be 0. This one is 0. And this one is also 0. basically, if you write down the binary expression, Boolean expression for each of the gates, it's quite clear that this what would be the output. The binary expressions for this one, for example, let me actually just do a little bit of cleanup here. The binary expression for this one is going to be, because I don't have any number here, that's why it makes it hard to write. So this is, let's just write this one as a sub 1 and a sub 0. So the Boolean expression for this line is going to be not a 1 and not a 0. This one is going to be not a 1 and a 0. This one is going to be a 1 and not a 0. And this one is going to be a 1 and a 0, which exactly showing 4 different possibilities, and all these actually different values that can be get from the a sub 1 and a sub 0. So you might actually just ask that when we might actually need decoder circuit, when we might need a multiplexer circuit. So the decoder circuit basically is going to help us to, for example, you have a couple of different circuits for example, for addition, for subtraction, for multiplication, for division, right? 4 different circuits. But each time you wanted to just apply one of these circuits, right? So it's just like you can, for example, you have a code for the, you have written, let me actually just explain that this way, that you are converting your algorithm, to, something that will be executed on the computer, on the hardware side. Okay, so there will be some code for all of these simple arithmetic expressions, arithmetic operators. For addition, there will be a code. For subtraction, there will be a code. For multiplication, there will be a code. And for division, there will be a code. So just assume that I'm going to have these 4 codes for each of them. And you can see that each one is exactly showing one specific and distinct operator that I wanted to apply. So you can pass 2 lines that show that which code you are saying, either you are saying addition or subtraction or division or multiplication, whatever. And on the output, this decoder circuit helps you to activate only one of them. So either this one or this one or this one or this one, just one of these lines will be activated. And then only that circuit at the end will be applied over the, for example, over the input, whatever is the input. For example, you have 2 inputs, A and B. You wanted to apply the sum operator over them. Either it will be actually just multiplication, so you would pass 0, 1, 0 to your decoder, and this line will be activated. And so this value will be actually just calculated. So decoder circuits helps you to select the main circuit that you wanted to apply at the end. What does the multiplexer do? Multiplexer helps you to choose the correct input. You can just think about it in this way, that you have 4 variables, for example, A, B, C, and D. Those 4 variables have been stored on some space in the computer. Let's just call them register. Don't worry if you don't know register. We will talk about it in the next chapter. So A, B, C, D, all of them have been actually stored in these registers. So these are going to be some binary numbers, right? But you are going to work on A and C, okay? So you are passing all these lines to a couple of multiplexers. For example, from all of these registers, I'm going to actually choose A first, okay? So multiplexer line is going to tell me that which value you are going to get. So for example, if you are in your selectors here, you are passing 0, 0, this register 0 or 0 will be actually passed, which you can think of it as, okay, this is going to be the value of the variable a. Another multiplexer will be choosing C, and these lines will be actually sent to, for example, a circuit which comparing A and C, and at the end you will be calculating, executing this comparison that A will be compared to C. So you need a multiplexer to choose A, you need a multiplexer to choose C, you need a decoder to choose the correct circuit for comparison, for example. All of these will be get together and you actually get the value be executed. So these are all different actually type of circuits that we need to be able to design our final computer. In the next chapter, chapter 5, we will talk about how we can actually use all of these circuits that we have talked about them, like the multiplexer, decoder, for example, the circuit for addition, comparison, and so on to, we are going to use all these building blocks that we have created in this chapter, in the next chapter, to be able to, to design an actual computer, in fact. So this is, in fact, the summary of this chapter. That's why this chapter is called the building blocks, because you are going to learn about all of these circuits and what's happening on a very low level of the design of the hardware. And in the next chapter, we will see a more high-level discussion about how to create a computer, the actual computers that we are working on using these building blocks that we talked about.